Hello, can you hear me?
Yes.
Okay. Okay. We should start. Do you have any question about homework? Are we good? Okay, that's fine.
Is it due on Wednesday or Tuesday?
I think 23rd is the submission day.
Oh, all right. Thank you.
Yeah. Okay. Mm. So today we will be doing radiation power density. Okay. So I will talk about little bit more about waves, but first I want to talk about this radiation power density and then we will move to it. Okay. Hmm, okay. So what is radiation power density? It actually, yes, I just wanted to confirm the name. Okay. So it actually is that like when we transport power or when we transport energy through EM waves, we are actually thinking about transferring the energy from one particle to another, right? So it should have some radiation power in it. Density, the name suggests that it should be per meter square, and or we are thinking an area from which it is radiating. So what I'm trying to say is, um, if I write, my voice is echoing 1 minute. Yeah, I think it's fine. Okay. So we know that, right? From one point to another. EM waves transport information through a wireless medium from one point to another, and power and energy are associated with electric and magnetic fields. So there, the quantity um, that describe the power associated with EM waves at any instant is called Poynting vector. So Poynting vector is the quantity that we use to describe the transfer of energy due to electric and magnetic fields. Okay, and it's an instantaneous value. So we say, when we express it in terms of Poynting vector, we say that W is E cross H, where E is a Poynting vector and it's also a power density. So at any instant, if we define it as it's a Poynting, we call it a Poynting vector. So if I define W, it's instantaneous Poynting vector, and its units are watts per meter square. E is instantaneous electric field, volt per meter, and H is magnetic field intensity, and that is A per meter. So these are intensities, or electric field, it's also the same. So these are the instantaneous values, okay? We are defining at any instant, and we are saying that E cross H is equal to the Poynting vector that is used to transfer power from one particle to another. Now, if we want to associate it with the radiation, like the power radiated, we, as it's an instantaneous value and its density, that is per meter square, we want to integrate it over the area, okay? So that's what we want to describe it as, a total power radiated. So I'm writing it as the total power crossing a closed surface can be obtained by integrating the normal component of Poynting vector over the entire surface. So we want to integrate the normal component of the Poynting vector over the entire surface, and that will give us the total power, or instantaneous total power. So if I just define this thing as instantaneous total power, it will be on the surface and ds, and we are talking about normal component, so it will be dA, like this unit vector of n represents the normal component. And if I think about it, if this is my sphere and this is a patch, or I am trying to find out the power radiated, so my power radiated will be associated with the normal component, right? That is coming out of the sphere. So I will be finding out the total power like that. Is it good? Okay, so here P is instantaneous total power, W, sorry, yes, watts. So sorry, it's the watts, or I should write it. And N is unit vector normal to the space or surface. And dA is infinite or small, infinitesimal or small area of closed surface, meter square. Okay, so that's what we defined as the total power. We had the power density, we multiplied or taking the integral of power density with the area, normal component of the area will give us the total power. So now we are concerned with the average power, okay? So this was the instantaneous total power, and now we are concerned with the average power. So in the time varying fields, average power density can be obtained by integrating instantaneous Poynting vector over the period and dividing it by one period. What it means that we have instantaneous Poynting vector, which is watts per meter square, but we want to find the average power density of the time varying field. So we will divide or first integrate it with on the time and divide it by one period. That will give us the average power density. It's not the total power yet. We are finding the average power density. Okay. So if I express it, it means that power average is equal to okay. I should write it density here first. Are we clear about this?
Is it dt? I mean, d lowercase t or d capital T?
It's a lowercase t. It's a
Okay.
time dependent, but we are integrating it over 0 to capital T, where capital T is your one time period.
Okay.
Okay. Is it good? Is it fast? Is it fine?
It's good.
Okay. So now we think that instantaneous, I find this word so big, time varying field can be written as, so I can write this as E x y z t is equals to real part of E x y z e j omega t. And similarly, h x y z real part of h x y z e j omega t. So after dealing with waves, I think we are very much familiar with this thing, okay? That the time varying field we define as this, that is real part of ej omega t, and xyz says that it can propagate in any direction of x, y, and z. Okay. Now, real part of, we know e j omega t is actually also equal to because that is cos ej omega t. In your book, they actually wrote the direct expression of the time varying instantaneous Poynting vector, but I'm trying to just drive it for you so we get it what it is, okay? So instantaneous Poynting vector, I'm just Poynting vector for time varying fields. Okay, so if I have this formula for Poynting vector, and I will do I will replace this as, so I am just, for the simplicity, I'm not writing XYZ every time. I am just writing EJ omega T, okay? Cross real part of HEJ omega T. Okay. Okay, and I will replace it as, if I am fast, you can let me know. I mean, if you want to write something and I'm going fast, you just let me know. So it's a cross product of both of them. I can also write it as yes, I okay, I will, okay. What I'm doing, I will explain, okay? Okay, so let's try to find what I have done here. So what I did, if I multiply ej omega t with e minus ej omega t, j omega t and minus j omega t will cancel with each other, and I will come up with E cross H, steric. Here, steric means what? Steric means the conjugate. Okay, is it clear? The first term,
Yes.
Louis, what do you think?
This looks good to me. I think I understand.
Okay, the first term is fine, right? Now think about second term. Okay, so if I think about second term, which I wrote it here, I actually skipped one step where I am trying to rearrange, but I'm just doing the reverse thing to see from where it comes from. So if you see E cross E minus, so when you are doing the cross, you are doing every term multiply with every other term, right? So here, if you see, E conjugate E minus J omega T multiply with this one will give me this. And there are two 1/2s, so I take one 1/2 outside. Okay, now comes the other part in which j omega t's will reinforce each other or they will cancel each other, okay? So in the first part, they are reinforcing each other when I am multiplying this thing with this thing. So it's become E cross H, EJ to 2 omega T. And for the second time, it becomes, no, sorry. This multiplied by this. Are we good about this?
Where does the 1/2 come from at the start of each of those? Not the one at the very beginning, but the other two.
Okay, so when you are multiplying E cross H, right? Your 1/2 will also multiply, right? Right? So it becomes 1/4. We will take 1/2 outside and the other 1/2 is still inside.
Okay, that makes sense. Thank you.
Mm-hmm.
Is there any reason why we just don't pull out the 1/4?
Yes. Yes. I want to make another expression. That's why.
Also, for the e to the negative 2jwt, is there a reason why it's on the magnetic field side rather than in the electric field?
Oh, 1 minute. There is one mistake here. What you said? I just didn't get it. Maybe what? Jonathan, what did you say?
Oh, the h is being multiplied by e to the negative j2wt. Is there any reason why it's on the magnetic field side rather than the electric field?
The terms with J2 omega T are in the magnetic field side. That's what you're saying, right?
Yeah.
No. I mean, they are not in any sides. It's just that we collected the terms without EJ omega T and with EJ omega T.
Okay, so it could have been on the other side as well, and still.
Yeah. They are not any, like when once they are multiplied, they are not on any side.
Okay.
Yeah. So anything else? Okay. So I'll write now. I can write it as, so when I'm taking the conjugate of the whole conjugate, it will ultimately comes the upper part, okay? One minute, I just want to confirm one thing. Yes, I think I'm confirmed. Okay, so what I did here is that I took the conjugates, okay? So conjugate of the complex number give us minus j omega t. So that's why I put the positive sign here. 1 minute, I'll tell you. So, okay, what I did here is, if I write conjugate of something, like if I write conjugate is this, right? Double conjugate gives the original number. So that's why I can write this thing as this thing. Is it clear?
Yep.
Okay. And similarly, I am taking the conjugate out as this whole thing out here. That's why I wrote it like this. So if you look closely at what I am trying to do, I am trying to make them same quantity with their conjugates, right? So if you see this thing, this and this is the same. It's just the one quantity is the conjugate of other, right? And similarly, this and this quantity is the same, but one quantity is the conjugate of other, right? Okay, now, if you remember that, I mean, I just don't move fast. So Maybe I
After
write
con-
it. Yes,
What happened to the negative in the last term?
1
The
minute.
last,
Yes, I will tell you 1 minute. So here, if you, I don't know whether you did it in the complex numbers or not, but if you have x plus jy, its conjugate is x minus jy, right? If this is your complex number z, and this is complex number z steric. Do you remember that?
no, but yes, this is helpful.
That's an honest answer. So this is the, actually, when we're dealing with the complex numbers, this is the conjugate of complex number, okay? So if you have ej theta, and this is z, its conjugate will be e minus j theta.
Okay, thank you.
Okay, so that's why we did this. Okay. What I was trying to tell you. Yeah. So what I'm saying was, if I can move a little bit up and you remember this thing where I wrote that real parts can be written as this, right? This is just what you write cos omega t. So it's just the same thing. Like when you write cos theta is equals to 1 by 2 e j theta plus e minus j theta. It's the same thing. Because real part of e ej omega t is actually the cos omega t. Do we understand this? Can we sink that in? So now if we put our attention here, I can write it as Okay.
Yep.
So yes, go ahead.
No, I'm just agreeing. Yeah.
Okay, so what I'm trying to say is that this part is actually one quantity is the conjugate of other. That's why we can write it as real part of E cross H conjugate and real part of E cross H EJ2 omega T. I mean, it's if it is not clear, you think it's complex, you can ask question. I'm here. I mean, it's not difficult. It's just looking tedious. All right. So it's easy to think that not easy to think. I think it's tedious, but it's just what we are trying to do is we are trying to build a relationship of time varying Poynting vector. Okay. So now if you see in your book, you see the same relationship. I don't know you have book or not, but you will see same relationship at 2.7. Okay. So this is, okay, sorry. So this is the same as your 2.7 equation in your book. Okay, so now I said that our Poynting vector is equal to this quantity. That is fine. But what happens to the time varying field? If you remember, I said that if you want to calculate average power, it's actually equal to 1 by t, 0 to t, E cross H dt, right? That's what we have said above. And this thing is our W instantaneous, or this thing is E cross H, okay? So when you are trying to calculate your average power density, it's actually is that when you integrate it over the one period of time, then it will give you the average power density. Now, if I want to plug this thing here, because instantaneous dt, then what will happen? Okay, I'm not going in the tedious integral, but let's see what we can imagine what will happen. When I will put that in this quantity, what will happen to this thing? What do you think? What will happen to this term? Because it's not dependent on t right now, right? This quantity is not dependent on t, okay? So it means that when I will put that in, it will give me t, right? Or should I do that? I'm not sure. Okay, let's see. So if I put all this in this thing, okay, yes. So what I meant to say that here I will get right? Do you have any question? Do you think it's fine? Or do you not understand?
When you take the second integral, when you get 1 over t times 1/4 the real e times h e to the j omega 2t, the 1/4 is coming from you bringing down the 2 from the exponent, right?
Yeah.
Why wouldn't you also bring down the omega in that case?
Yeah, I think so. Yes, you're right. Yes. Are we clear about this? So I will come back with this thing. Because t will cancel with t here. But here, if you pay attention, what will happen? If I replace ej2 omega capital T, that is the whole time period, minus 0, right? So these two quantities will cancel each other because they will both get us 1, because it's the whole time period we are covering. It's like the ej2 pi and E0, real part of that, okay? So that's why we are canceling them. And the only thing that will remain is this thing. Which is our average power density. So what this shows us, that it shows us that in the time varying field, our average power density is the real part of the Poynting vector, right? And real part of the Poynting vector is what is radiating, okay? So it comes us to think that what is the imaginary part of Poynting vector is. The imaginary part of the Poynting vector is the stored energy. So if you are thinking that this real part of the Poynting vector radiated energy right? So the counter argument is that imaginary part of pointing vector is stored energy. It's kind of that sometimes what happens is that you are transmitting power, and something is not right, it's not radiating, it's going somewhere else. That is where it is storing itself, and it is radiate like because we have to follow the conservation law. So it's going somewhere else as a stored energy. So that's what we are trying to establish. So there are three things we said, okay? One thing we said is that our radiation power density is equal to the cross product of E and H, which is also called as Poynting vector, right? But we said that our Poynting vector or radiation power density is the cross product of E cross H, right? The second thing we said that when we think about time varying fields, our average power density is real part of Poynting vector, right? The third thing we said that if we think about radiated power, that will be the integral of power density, right? So we said these three things. If I just summarize it here, let me come back to this. So what I said here, that our instantaneous Poynting vector is the cross product of E and H, where instantaneous Poynting vector is the instantaneous power density, right? Are we clear about this? Bryce, what do you think?
Yeah, this is clear.
Okay. Then if I go down, we said that total power is the integral on the area of instantaneous total power is the integral of the area of instantaneous power density, right? Okay, so we are good with that. But we did another thing. Instead of finding total power, we come back to the power density, average power density, where we said that for the time varying fields, average power density is that if you integrate it, it's over one time period. Now we developed expression out of it, and we said that for time varying field, our average power density is the real part of Poynting vector or real part of E cross H conjugate, right? So technically, now I will try to find my radiated power or average power of time varying field, okay? Okay. Is it fast? Is it fine?
I think it's fine.
Okay. Um, okay. Another point I want to make is So in the far field region, in the far field region, antenna's power density is always real, okay? So because we are all the time talking about the real power that is radiating. So power density associated with antenna in the far field region will be real, okay? And it will be referred as radiation density, sorry, not intensity, radiation density. Okay. So now I want to find radiated power. Or average power. So I can write it as P rad or P average is equal to so it's the dot product with it's the normal, it's normal and the area that we are thinking about. So if I just write it as, it will be P rad. Another thing is that when we are measuring the power patterns, we are actually talking about this radiated power, okay? We will see how we will think about it, but normally we do that. Okay. So if I write it like this, let me try to find power density of or radiated power of isotropic radiator first. Isotropic radiator means that it will radiate in all directions, all angles. So it's like a sphere, right? So if I'm trying to find its radiated power, it will be I will take 0 to 2 pi for phi, 0 to pi for theta. I will write it as AR W naught R. I will tell you what it is. And then I will do AR R squared sine theta d phi. So what it is, actually, we are saying that if this is my isotropic radiator, and this is the patch of a surface, like of an area, and it is pointing out in the direction of R unit vector or AR unit vector, then if my power density is also pointing out in the same direction, then I will write it as AR W naught R dot product of AR R squared sine theta d phi. So my ds or dA, which I defined before for the sphere, is this thing, right? But the thing right now here is that its direction is AR with AR unit vector. And my power density for isotropic radiator is also AR. I'm not defining what it is, but just AR W naught of R. So now if I try to write it, it will become I think we solved it before, and it was, I think, 4 pi in the last time when we solved it, right? Just a minute, let me see. Or I can solve it again. So it's W naught R square. If I am doing phi will give me 0 to 2 pi phi, and theta will give me 0 to 2 pi minus cos theta. It is minus cos theta or cos theta? What do you think?
Minus cos theta.
Okay, so it will be 2 pi, then it will be minus cos pi plus cos 0. Yes, okay. So it will be Are we good about this? Are we good? So actually what you have done here is you actually found out a relationship between isotropic power radiators, radiated power, and power density, right? So its power density is radiated power by 4 pi r square. Okay, so that's another relationship we found for isotropic radiator. Okay, actually, I want to do one more example, but we are good about this. I mean, you just have to take the integral, surface integral of power density to find out the total power. Or maybe let's stop it here, okay? I will do this example next time. Do you have any questions about homework? I have this fourth B and C. You think you are able to do that? You were able to do that? Fourth in homework, fourth B and C. Do you have any trouble in it? You think you're good?
I did actually have a question about that.
Yes.
We're finding out when the wave is interfering constructively and destructively. Is that going to be like a range of values, or is that going to be like a singular value?
It can be range of value, yes, but range of value because you will come up with the number of angles, right? Like 2n pi or something like that. I'm just formalizing what you want, what you will be doing in fourth B and C, okay? I'll not do the whole thing, but I'm just trying to anticipate that you know what fourth B is. So I'm just trying to do that. So fourth B wants you to constructively, like in fourth B, waves are interfering constructively, and you have to find at certain time the corresponding value of the total wave. So what they have given is that if you do this, it will be maximum. And when the waves are interfering constructively, you will just add them. So I think what I am having it here is cos 0.4 pi minus 30x minus cos 0.4 pi plus 30x, right? Something like this. So you will add them up. You are adding them up because one of the thing is minus. So it will always automatically coming as minus here. And so when you are adding them up, you think of adding it like that. Sorry. Cos x minus y plus cos x plus y. So what this comes as? This comes as not mine, it's minus here. It comes as 2 sine x sine y, right? So when you do this, you will just replace your values and find the maximum value for ys max. Maximum value for ys max will be when they will constructively interfere, means when your sine will be 1. So just do that and you should be able to find it.
Will our homework be graded for correctness?
Yes, I will just see the method. Of course, if you have done right, you will get the full marks, but it's not that if you have not done right, you will not get marks. It's not like that. I will give the grades for effort. Okay. Okay, sounds good. It's just okay, so I have, I think, an interactive questionnaire for you. Let me, okay. But before that, there is one person who asked me question. I want to address that too. 1 minute. So are we good about this? Do we have any questions? You can
I
ask
have
me.
another
Yes, go
question
ahead.
about the homework.
Yeah, yeah.
Problem number 2, where you're going from the phasors to the time functions. I was a little confused about like with like the E, like where you're like adding or subtracting a pi and like how you determine that.
Okay, let's do the first question, maybe. 1 minute.
Yeah, either the first one or the second one would be fine.
So that one was -5 EJ pi by 3, right?
Yes.
Okay, so 1 minute. Can you see? Yes, 1 minute. So this is problem 2. Let's say do A part. So it's V -5 EJ pi by 3. So what we will do here, we want to write it in terms of time domain function, right? So we can do this. Right?
Right.
Is it fine?
So that's the answer. You don't have to, because don't they ask for a sine function? So do you have to change that from cosine to sine?
They didn't ask you for this. Oh, sinusoidal function you meant?
Yeah.
Sinusoidal is cos and sine, both are sinusoidal.
Oh, okay. Okay.
Okay?
Wait, would you be able to go over part B as well?
Okay. So there is one more way of doing the first question, but it's okay if you do this like I have done. Okay, so now in the second part, there is a little bit trick. Okay, so this J is actually EJ pi by 2. Okay, why? Because if you do this cos pi by 2 plus J sine pi by 2, it will comes as J. So that's why you can replace it as EJ pi by 2. And this will become 6 E minus J pi by 4. So it will become minus J pi by 4 plus J pi by 2.
Okay, yeah, that helps. I was getting lost on the pi by 2 part.
Yeah.
Yeah,
And
I
this
see that
will
now.
become J pi by 4, sorry, plus J pi by 4 when you add them, right? Yeah, just take this LCM and this will be J pi by 4. And this will become 6 cos omega t plus pi by 4. Okay?
Yeah, thank you.
Okay, any questions? Okay, so we are good about this. Okay, let me talk 1 minute. I need to address one question, I think. Okay, so I actually did these slides for longitudinal and transverse wave. We may be doing something sometime else, but I'm just trying to address one question. Okay, so you saw, can you see my slide, like these slides?
Yeah, we can.
Okay, someone asked me this question, that why is that happening, that you have X and Z here, right? So X means that your direction of propagation in X direction, but the unit vector shows that this is in the Z direction, right? So what happens is, this is just the electric field, and the propagation of wave is both electric and magnetic field, okay? So what happens is that whatever is the direction of electric field and whatever is the direction of magnetic field, the result is actually E cross H or E cross B, which is perpendicular to that direction. So it can happen that your wave is propagating in some other direction and your unit vector is in some other direction, okay? Because the direction of propagation of your wave is the perpendicular to the direction of propagation of your electric field and magnetic field. That's why you are seeing the difference in the unit vector and the direction of propagation. Okay? Is it clear? Yeah, let's say here, if you think about in this question, like in this electric field, I mean, it's not related to your homework, but it's just the understanding what I'm telling. So it's, if you see here, the direction of propagation of your wave is X, like in this. Can you see my mouse? Right. So here, direction of propagation of your wave is X, but the electric field direction is in Y at that very instant. Right? So that shows the direction of electric field at that instant, but the direction of propagation is different. Are we clear about this?
Yes, this is clear.
Okay. So, okay. Let me see, do we have enough time, or maybe we will do it next time. So I think we will do at the start of next class, because right now we have less time. So just do the minute paper for me, and that's about it if you do not have any questions. Okay, so, oh, one more thing I want to ask. So have you done take-home exam before?
Yes.
Yeah.
How that works? I mean, how much time you normally have if you have